Well, good morning, everyone. It's my pleasure to be here. It's used to be my school long ago, so it's always a pleasure to come back. And thanks for inviting me to talk about the Mars program. I'm not sure you're really aware that we're living a very special time these years. We're exploring Mars as we ever done it before. It's really amazing time, so I'm going to show you what it is all about and why do we do all these big programs to Mars. It starts with one question. What question? That question is life on Mars. It's not a simple question. It's really the goal. I mean, it's an ultimate goal, I would say, of our planetary exploration. It's to try to find life somewhere else than on Earth and possibly on Mars. And the question with this problem is can you reduce this big question into some small pieces that you can make some research program from. So how are we going to organize our space program? We just going to say, okay, we're going to look for life. No, it's more complex than that. It requires many different missions. So how do we organize our space program? How do we make it readable? It's very important. You have a lot of people who are looking after us, and they want to know. They want to know how we do it, how well we're doing or not, and so that needs a bit of work. And how to keep the momentum. Each time you do a discovery, you have to make sure that people think that you need more money to make new discoveries. So keep going. Okay, let's start with Mars. Mars as a planet. I'm sorry for the people who know so much about Mars. This is on the left, the Earth, on the right, Mars. As you can see, it's a smaller planet than Earth. It's rotates around itself in approximately 24 hours and 40 minutes. And I should tell you that 40 minutes is a pain in my life because I'm living on Mars time. And it's every day you take another 40 minutes. And it's really a real pain. It's further away from the sun, so the year is longer. By the way, we call a Mars day a sol. So it's called a sol, S-O-L. So, for example, when I'm working on Mars time, I say yesterday, well, actually, yesterday becomes yester sol. So I'm working tomorrow, and tomorrow is going to be soloro. And sometimes we go on vacation, so it's called a soliday. So we have to put some new names. The year is longer. The year is 667 days, but it's sols. So 667 sols, and it's more days, of course. It's further away from the sun, so it's a cold planet. Don't expect it to be warm. You will see roughly, it can go to zeros, but most of the time it's minus 50 to minus 90. Doesn't get so much light, less gravity, and there's an atmosphere. The atmosphere is very important. We think it's very different from the one it used to be in the past. But the one it is now, it's made of CO2 mostly, and it's slightly less than 1% of the pressure we have on Earth. So we call it a residual atmosphere. So it's not a great one, but it's important for what's happening on Mars. If now I look at the topography of this planet, this is on top left, this is the northern cap, top right, the southern cap, the mid latitude at the bottom. You can see the scale. When it's green, yellowish, it's roughly what we call zero altitude. We have to pick up one crater and say, this is a zero. There's no other way to find a reference. Everything that is above goes to 4 kilometers, 8, 12. We're talking mostly volcanoes. Actually, we had to cut down the solar scale because it would go to 28 kilometers. Some volcanoes are really high. Well, it's not a surprise. When you have a small planet with less gravity, volcanoes tend to go higher. That's it. You have also some craters, mostly in the southern hemisphere. You can see that the southern hemisphere altogether, it's roughly 4 to 6 kilometers higher than the northern hemisphere. Don't ask me why, we don't know. We have no idea why there's such a dichotomy between northern hemisphere and the southern hemisphere. It's one of the major questions on Mars that we don't understand. So you see craters. One of them, like Hellas, goes to -11 kilometers. So a lot of topography, but it's not a surprise. Small planet, you get usually a larger range, at least for rocky planets. Okay, let's look now at the water. Because the water is a very important, of course, ingredient of life, but it's a very important ingredient of planets. And if you give me two planets in a universe, the first question I'm going to ask you is which one has water? When I say water, it's liquid water, because it can really change the fate of your planet. We have, of course, on Mars evidences of water. Don't tell me we've discovered water on Mars. We've done it 30 years ago, okay? And journalists keep telling me, oh, you've discovered water. I say, no, it was long ago. We have a lot of evidences of water on Mars, and these one are called the outflow channels. The outflow channels are important because it's a lot of water that flow for a very short time. As an example, here on top right, you can see that the flow we're going around the craters, it's kind of used. On Mangala Valleys here, you can see some flooding area, and it's very similar to what we have in the Sahara, for example, where there's no water, and suddenly water is pouring like crazy, and then it stops. For that, we found that comparing the different regions, that it appears at all times. How do we know the times? Well, it's simple for us. We measure the number of craters, the crater density. If there are a lot of craters, it's old. No craters, it's young. That's easy. That's how easy we do it. So we found that we have this outflow channel for a very short time. It can last, well, it's at all time, any time of Mars life, but it can last for usually 2 to 3 weeks. It's very short. A lot of water for a very short time. That's what is an outflow channel. What's interesting from the physics is that to get an outflow channel, you don't need a thick atmosphere. You don't even need a thermodynamical stable state. It can be, the water is flowing, and even if there's a little atmosphere at the same time it's boiling, and it's going to evaporate. Where is the water coming from? Probably from a pocket under the ground. That releases a lot of water. So it's interesting to have these outflow channels, but it doesn't tell us if water was really stable on Mars. What would be more interesting is to find evidences of fluvial activity. And we did. We did many times. Remember that today, if I pour a little of water on Mars today, liquid water, it's not stable. It's going to evaporate right away. In the past, it was not the case. Look on top left. Variable valleys, you can see the delta. We call that fluvial activity, okay? And it's like in Yemen, for example. Equus Plateau was same kind. So we've been working on these different valleys and delta. We've measured the slope and compared the slope to the Earth. We measured the density. The density is a ratio of the length of the traces we have divided by the surface. So we've compared with Earth, and we find that it corresponds mostly to the density is 0.2 to 1 per kilometer on Mars, and it's roughly like what we call a dry river on Earth. So it's not like an active system now, but it could correspond to what used to be active in the past and has been eroded with time. And if we look at the rate of flow, we had between on Mars 300 to maybe 5,000 cubic meter per second, and that would correspond to a mid-size to small size between La Loire or the Danube, in between these two ones. Nothing like the Amazon, but probably that kind. So in the past, Mars was certainly a different planet. It had liquid water, and we can find that only on old terrains. Or it had outflow all the time. Two things that could be different. And we also find some sediments. From orbit, we're looking with spectral imager, like in the infrared, for example, and we have an excellent one on Mars Express by Jean-Pierre Bibring and François Poulet, and it's called Omega, and it's looking down in infrared, and I found signatures of hydrated minerals. We call them phyllosilicates. Why you call them phyllosilicate? We call them mud, argile. So to create a phyllosilicate, you need to run a lot of water or have stable liquid water on top of any kind of rock, potentially any volcanic rock. And after years and years, thousands of years, you turn that into mud. And that's what we found on Mars. And that's very interesting, because if you look how it's spreading everywhere, we say, well, it's not in one place, it's all over Mars. Actually, we don't understand why it's on the old terrain and not on the new terrains. So there are a lot of questions we have, but it tells us that, yes, in the past there was not a local one now, but a global water. So it was not an ocean, but it was liquid water was probably spreading all over Mars. And if you bottom left, this is called the Ebers Valley crater, and it's a delta again of sediments, and it shows that the sediments are trapping, because of their mineral phases, the history of water on Mars. So you get the whole picture of water. You can see it was mostly in the past. Today, do we have? I say no for liquid water. There's no liquid water on Mars today. We found some ice near the pole. Our top left was Phoenix. It was one of the landers when it's scooping on the ground, and below the scoop and the regolith, there was ice water. There was water in the ice cap. There was what we call here the gurneys and the RSL. These two things are not really water. They had brines, so it's a water with a lot of salt, and that's why it's a very special case. But today, all the water I can find on Mars is really ice. Okay, so let's put that back together on a time scale. The time scale of Mars starts here. It's now. We call it the period, the Amazonian, and go back in time, just like the Earth. Planet Mars is 4.5 billion years old, just like all planets. What it shows on top, the outflow, I told you about the yellow one, they appear all the time. It's good to know. But it doesn't tell us much about the stability of water, because it could be out of an equilibrium, a thermodynamical equilibrium. If we look at the global valley, the blue one, which is where we see this fluvial activity, it's mostly around 3.8, maybe to 3.2 billion years. That's probably was a time where this fluvial activity was happening. We have other things like the sediments. The sediments appear at the same time or older for the fluvial sediments. The sediments we get this past 3 billion years are really from the wind, Aeolian activity. So you see that the difference was the story of Mars is kind of strange. In the past, we had water most of the time, fluvial activity. We don't know. We have a minimum of 100,000 years, but it could be millions of years. We don't know. We had hydrogen minerals in the ground. We have a global equivalent layer of water of approximately 500 meters. You know, you imagine in your head that you take the planet, you remove all the mountains, all the craters, you make it in a very nice small ball, and say, how much water do we have? On Earth, you have what, 3 kilometers of water? This is our global equivalent ocean level of water on Earth. It's 3 kilometers. Well, we think on Mars, there used to be 500. Now, if I say what's left today, well, there's a little bit of ice. There's a little bit of water in the atmosphere. We need it. But if I precipitate all the water, it's only 16 microns, so it's almost nothing. We have some transient activity, some hydrogen minerals, they are still there. And we don't know how much is the equivalent of water, but probably something like 50. We've lost most of our water. So what it tells us is that in the past, Mars was different. Let's put that into a pressure to temperature diagram. You know that very well. It's the stability of water. You get the ice on the left, top liquid, vapor on the right, triple point. You know that. If I take the one pressure, one atmosphere, and if I warm up an ice cube, it's going to warm up, it's going to become liquid, and if I go down, it's at 0 degrees. Well, that's by definition of 0. You warm up your liquid water, It's going to cross this other line and become a vapor at 100 degrees, at the definition of 100. So you know that way very well. This is where Mars is today. Mars is there, which means it's ice. Okay. In the past, I have to imagine that Mars was somewhere else. It had to be in a liquid region. It had to make possible all this liquid water on Mars. But it's not easy to warm up a planet. How do you warm up a planet? You don't bring it closer to the sun. Okay? The only thing you can do is to increase the atmosphere, increase the density of the atmosphere. So we have to imagine that in the past, the atmosphere was denser. But if it's denser, you see it's going up. Does it really help you to go to the liquid phase? Well, yes. If you do the gas, that is creating some greenhouse effect. And that's exactly what happened. The atmosphere of Mars used to be denser. It used to have the, and at the same time it was creating a greenhouse effect that was warming up the planet. To imagine that, our models so far show that with 2, maybe 3 bars of CO2, we can make that. So that is the story of Mars. Water in the past, denser atmosphere. So the atmosphere disappeared, and we would have to understand why and how did the atmosphere disappear. And at the same time, I say, when it disappeared, the planet became kind of dead. I mean, Mars is a dead planet these days. For the past 3 billion years, nothing happened. It's cold, a little windy, not like in the movie, okay? Don't believe the movie The Martian. It's a great movie. We love it. But there's no wind such as the wind that it started at the beginning when having, up to the point to elevate rocks, okay? It never elevates more than a tiny, tiny amount of dust to that height, okay? So the movie is good, but that part is wrong. Okay. These days, not much is happening on Mars. So why does it make Mars interesting? It makes Mars interesting because when we compare it to the Earth. Look at the bottom. Same thing. Now, so we are here. I mean, this is really where we are, okay? And remember, the dinosaurs and things like that must be here, okay, somewhere here. We as humans are in the thickness of that trace, okay? The black one, okay? The complex life is what, the last 700 years, 500 to 700 million years? That's complex life, multicellular life. It's all we know about life. The rest before, well, we know a little bit, it's called the bacteria and unicellular. We don't know exactly when it started. Well, we know there were traces of life at 2.7 billion years ago. Now we're pushing the limit. Used to be 3.2, now it's maybe 3.7. There was a good paper last year in Science to say that, yes, traces of life are at 3.7 billion years, okay? But it's very simple life, bacteria, okay? And it took the life approximately more than nearly 3 billion years to come something that is really become major, and we create something we love, fossils, for example. Don't expect a fossil more than 700 million years ago. Okay, so that's the story of life, the start of the life on Earth. We don't know so much. The problem we have with Earth is that Earth is a very active planet. There's what? Plate tectonics, there's a wind, there's a water, all sort of erosion, there's life. Life is eroding the ground. Which means that Earth has no memory. It's extremely hard for us to study all that period, and especially the time when it started. Well, we know when it started, the Earth was very hot, because it's formed for accretion. So it was super hot. Okay, cooled down, there was water, and suddenly there was life. Okay, how did it happen? We don't know. When did it happen? We don't know. We don't know mostly because we have no memory on Earth. We're really a terrible planet. It's a planet of the present, not of the past. And the reverse, look at Mars. For the last 3 billion years, nothing happened on Mars, more or less. I mean, some volcanoes, some outflow channel, we've seen that. Few things, but not really. the interesting part, and what we really see now on Mars, we see that window of time, the first billion years, that does not exist anymore on Earth, where probably the same thing happened on Mars and on Earth. So to make it simple, Mars, studying Mars, is the best way to find, to understand the story of life and how the life emerged, possibly on Earth and maybe on Mars. That's why Mars is so interesting. It's like looking in the past of a planet. You got that? So, usually I have to do that story very short, because I have to do it with some politics and say, okay, so now what? I say, give us money, and we make a very nice exploration of Mars, I mean a program. How are we going to do that? We're going to start with first point, follow the water. We're going to tell you about the water. I think you understand that part now. Search for water. I mean, we try to give it a theme. Second, we say, okay, we're going to explore the habitability. If there was water in the past, were there all the different conditions to make an habitable world? And the third is searching for a sign of life. So we really try to organize our program. We're not the first thing. This is, I was trying to 73 missions to the moon, 43 to Venus, and now 44 to Mars. And we keep increasing on Mars. I mean, it's exploring, it takes time to explore the solar system, but we do have program. We have a lot of these different projects, and actually it's great. So the Mars program today, how many spacecraft do we have today? 1, 2, 3, 4, 5, 6. We have 6 spacecraft today around Mars. They all are fine. Mars Odyssey, Mars Express, MRO, and Maven from the US, Mangalyaan is from India, TGO is from Europe. It's the last one, and it's working perfectly fine. All of them, they are rotating around the planet, and some of them are on very elongated orbits, some of them on very circular orbits. They look at the planet, and they're working fine. At the surface, we have 2 rovers. We have Opportunity. Opportunity is really old, okay? It's more than 10 years old, so it doesn't move very well. It's pretty crippled, but it's working still. And Curiosity is the young one. It's already more than 4 years on Mars, and it's working fine. But sometimes it has problems, like every rover, so we're fixing. But we have 8 spacecraft now today on Mars. It's never been done before, of course. We went slowly from the follow the water, I would say between 2000 and 2000 and maybe 8, turning down into the habitability. This is where we are now, like Curiosity, Maven, TGO, looking for habitability, and then slowly we're going to drift with a seek of searching for life. What's the future? In a year from now, we're going to launch InSight. InSight is an amazing mission. It's probably the most difficult one we ever done. The goal is to land a platform. On that platform, there is a seismometer. The seismometer is partly built here in this school, and everywhere in France, England, and Switzerland, and Germany. It's quite a challenge. It's certainly the most difficult instrument we ever done. So that's to explore a seismometer, the interior of Mars. We don't know anything, honestly, about the interior of Mars. And then two new Rover are going to come, ExoMars and Mars 2020, launch in 2020, and they're really going to go for signs of life. In parallel to this program, for the water, habitability, and signs of life, we are preparing the future of human exploration. We need to land at some point a man, woman on the on Mars. I hope it's going to be one of you. Not sure, but we'll see. It's not easy, okay? For people who tell you yes, it's going to be in 2 years, don't believe them. People who tell you it's going to be in 10 years, don't believe them. Okay? We don't have the technology, and by the way, we don't have the money. Okay? If people tell you one-way trip, don't believe them. You never have a government that's going to sign for a one-way trip. No, not ethical. Okay, forget it. So we need to have a mission to Mars. My guess is that it's going to be an orbital mission first. Okay, we put them astronaut on orbit, they play with rover on the ground, they come back. Okay, 10 years later, we try to land them. So far, landing someone on Mars is difficult. Living off Mars is impossible so far. So it's quite a challenge, but we're really looking at that, and we're getting ready for that. Okay, so these are some of the orbiters we have now. I like Mangalyaan because it's the one from India. I'm not sure the science is there yet, but it's an amazing achievement in terms of technology. TGO was great. TGO had a small part that was supposed to land on Mars. Schiaparelli, maybe you followed that last year, October of last year, it did land on Mars. Not in one piece. Okay, it did, just like Beagle. We've tried it twice in Europe. We failed twice. Okay, we failed Beagle. We didn't know why we failed. We had models say, okay, we burn into the atmosphere, everything. Until 10 years later, we took that image of Beagle. Beagle landed in January 2004. We saw it had crashed. And then when MRO took that image, we realized that no, Beagle had landed. It had even opened its solar panels, but did not call us back. So there was a problem, we don't know where, but it had landed. But I could not say it's a successful landing. Same from Schiaparelli, it had landed, except it looks like a software problem. It looks like the software received a data point that say I'm off course. I'm out of the limits, so it was an error in the fault, what we call the error fault tree. Took the wrong path and decided that it had landed, so it shut off everything. It was more than 1 kilometer altitude, so shut off the thruster, everything, and went down. It even started the payload. I have a friend, a poor friend, who had built an instrument for 10 years, and it was on Schiaparelli, so not good for him. But actually for 8 years, because he told me that it started the payload, sent back some data, so he has 8 bits. 8 bits of data to say, oh, I'm okay, to say, hey, ready to go. 8 years, 8 bits. That's what you get. Of course. Landing on Mars is certainly very difficult, but sometimes you have success, and I should say that the only one who had really success are the US. They're absolutely amazing what they've accomplished. They put the first one was Sojourner with only half a kilo of payload. Then Curiosity, Spirit and Opportunity with roughly 8 kilos of payload. Curiosity, you have now 80 kilos of payload, and we have in the meantime Phoenix, which was a fixed lander, and actually InSight is going to be exactly the same. So landing is difficult, roving is very difficult. A little more about InSight. Just show you on top left the seismometer. Again, the most complex instrument we ever done. The most expensive one, it takes a long time to do it. They're really fighting, but they're doing okay. They're getting ready to be put on the spacecraft. It's going to be launched next year, and again, it's to understand what was what is now the internal structure of Mars. They're going to use impact and quakes to study that volcanism and so on. Okay, and just to finish up, the next rover, there's going to be the ExoMars. So ExoMars is 2 parts. One was TGO and Schiaparelli, that's done. TGO is working fine. I've seen some good data. It's going to take a little bit more time because they're using the atmosphere to circularizing the orbit, so it takes about a year. So they're not in the final orbit yet. And so TGO is fine, but the second part is called ExoMars 2020. It's a rover with a drill. We're going to drill deep in the ground, 2 meters, bring back a sample, put it into the rover. And there we have an instrument, like there's a laser instrument we're working on here, but there are other instruments to study the samples. ExoMars, Europe on Mars again, and US on Mars again, Mars 2020, very much like Curiosity. I'll come back to that. Well, I should tell maybe a little bit after that. A little bit. Other projects, that's not all. Some people are really looking at Mars. So what do we have? India, once they want to fly Mongolian 2. Well, why not? This time they say we want more science. So the first one was really most about technology. And they did great. This time they say, okay, let's do now science. So they're concentrating on the payload. They try to get a good payload. When they have that, they're going to build, I'm sure, a nice spacecraft around the payload. Japan. Well, Japan, what they love in Japan is to make return sample. They've done it. Hayabusa 1, they are on the track for Hayabusa 2, and now they want a return sample for Mars. Well, they know that it's very difficult to do that for Mars. There's a bit of gravity. And so they say, well, why don't we get first to Phobos, one of the moon. Get a sample from Phobos. There's going to be a lot of Phobos, but probably a little bit of Mars too, because each time there was an impact on Mars, it could send in the air a lot of material from Mars that could be captured by Phobos. So there probably a few fraction of a percent of what we could bring would come from Mars. And it's easier to do a return sample. So Japan is looking at return sample from Phobos. China is looking at doing it. Well, of course, we know nothing. We've seen some nice image, but they're going so fast. Remember, they're going faster than any country in history. Okay, the way they put man in space, and now they are a small space station. The way they explore the moon, and they land on the moon. They have a rover on the moon. What they're going to do on Mars is probably amazing. So we're looking for that, and we don't know exactly, but apparently in 2020 they may have something on Mars. What is more amazing even is the Emirates. They want to celebrate the 50th anniversary of the country, and for that they want an orbiter on Mars. Well, why not? It's a great idea. They're smart people. They have a lot of money, so we'll see if that's enough. Okay, it's interesting. Okay, so where are we now? Follow the water. Well, that was the third theme. I would say, consider it done. Yes, we understand more or less the water, not everything, of course, but we have a good understanding. Habitability. Okay, second part. I need to work on habitability. We're going to do that next. But it's nearly done. You will see that. We think we can say that in the past Mars was an habitable world, and I come to that. Searching for sign of life. Well, we need to do it. But at the same time we say, I need to do it in 2020. I'm asking the question, is this really possible? When you look at the Earth, you see that signs of life in the past were so small, so tenuous. We're looking for bacteria that were living here 3 billion years ago. This is not easy. So we're not even sure we can do in situ. So what we're looking at is to do a return sample mission. Because whatever we do on Mars, we know that we can do it 1,000 times better on Earth. So the idea this time would be landing on Mars, grab a sample, put it there back in a rocket, which is not easy to land a rocket on Mars, we've never done it before, and fly the rocket, and then launch the rocket from Mars, put the rocket in orbit around Mars, then you have another spacecraft that comes and grab the sample, return to Earth. We need at least 3 missions to do that. It's called a return sample. But for that, we know that if we do that mission, we know that it's going to take a long time. But the science we're going to do in our lab on Earth, it's amazing compared to what we can do in situ. So we know the solution to our problem is to return a sample. Okay, so we're working at returning the sample. We don't have the technology. No one has the technology so far to launch a rocket from Mars. We don't. No one has that, and so we need to develop that. So, but at the same time, the Space Agency, when they know as scientists, say, guys, we've been there before, okay? Show us first that it's worth to return, a sample from Mars. Okay, so they reverse the problem. Because we tell them, oh, you don't have a rocket, please, can you develop a rocket to return to Earth? Say, no. Show us first that it's worth returning your sample. So you will see the next mission, it's called Mars 2020. It's going to do the sample. Yes, it's going to do it. It's going to put the sample, get it ready, and then we come back to the politics and say, guys, now it's a good sample. Go and get it. And I'm sure they will do it. So it's kind of an alternate view of the problem. So we have that Mars 2020 mission. It's going to explore the geology of Mars, kind of curiosity-like. look for habitability, kind of curiosity-like, but it's going to do biosignature. This is much more. We're going to try to find if there are some biosignature of some minerals, for example, that have been created by bioactivity, and that could be a sign of life on Mars in situ, but more than everything, return a cache sample. So we're going to take samples like this one, put them into a box, put it on the ground, and then leave it there. Okay? And we're going to prepare for Mars exploration. What is Mars exploration? This is this guy here on Mars. Why do we do that? Because each and every one of our missions had to be ready. I mean, it's one step at a time, okay? And we have MOXIE on Mars 2020. MOXIE is going to create oxygen. It's going to take CO2, burn the CO2 at approximately 800 degrees with some process and some catalyst, and produce oxygen that is pure to 97%. So we're going to produce oxygen. I think in 2 months, we're going to produce enough oxygen for an astronaut to survive for 1 month. Well, it does not make it yet, but it's a good start. The instrument is that big, so that's how we prepare exploration, the future exploration. In the meantime, of course, we're going to dream. This is our local hero, as everyone knows, heroes of social network, as it looks like. Great astronaut, great guy. I made him a gift. I said, if you go to Mars, please do something for me. And the gift was given to him by the director of the museum here, and another astronaut, Claudie. And the gift was a Mars rock. So he has in his pocket a piece of Mars. Okay, it's good. That rock. Okay. A couple of billions, 3 billion ago, there was on Mars, there was an impact. So some body came from the space, impact on Mars. A lot of rocks went up. Most of them fell down on Mars. Some of them went in orbit around the sun. Okay, turn around the sun. They fell. It happened that one of them fell on Earth, in one of our deserts, where someone about 30 years ago found it. We could, in our lab, we could identify that it was coming from Mars. We do that by looking at the interior, looking at the chemistry, especially the gas phase. So we know, as part of our millions of meteorites we have on Earth, some of them are coming from Mars. This is one of them. So this rock has traversed 2 atmospheres, Mars out, Earth in. Okay, and I gave it to Thomas. So he went another atmosphere to a space station. Of course, he's going to bring it back. So this rock will have traversed 4 times the atmosphere. Okay, and I'm sure you guess what I'm going to do with it. Of course, we're going to put it on Mars 2020, so we send it back to Mars. Well, this is our way to do the return sample. I know it's a long way, but so that's our plan. When Thomas is bringing it back, we cut it in pieces, and we send 1 piece back to Mars, and this rock will have traversed 6 times an atmosphere. And I can guess it must be a record in the universe. Okay, we'll see that. Okay, so that's just a fun part. But Thomas wants to go to Mars, so I say, well, give it that's the best start you can have. Okay, for that, we need to return to Mars, and that's going to be Mars 2020, very much like curiosity. That is curiosity. I'm not going to talk about curiosity because I don't have so much time. It's working okay. Well, sometimes I need to fly tomorrow to JPL because we need to fix something. Honestly, it's getting old. That's what it is. 4 years in space, very cold at night, minus 90, 0 degree or minus 10 during the day. It's a lot of thermal excursion, a lot of dust. But it's working kind of fine with our traverse. We went very slow at first, did approximately 1 kilometer in the first year. Now we've done more than 15. So we went to Yellowknife, Darwin, Cooperstown, Kimberley, all these different places. And here, along what we call the dunes, we've studied the dunes. And about a year ago, we traversed the dune, and we're going to some place called the Hematite Ridge. In terms of soil, tomorrow is soil 1600, 1600. That's how far we've gone. We're not finished. I really hope we're going to live another year and a half. It's a minimum. Extra will be better, because we need to explore these different minerals we've seen from orbits. So Curiosity is doing kind of okay. The view is absolutely spectacular. So we're going to climb a small mountain at the center of the crater. The crater is called Yale. So we're really climbing. I mean, these days it's steep. I mean, it's very interesting. This evening we're coming to another dune. So we're going to traverse the dune again, a sand dune again today. This was the first one we could see. It's called Bagnall Dunes. We did a lot of good science, a lot of good papers actually. They're going to be published next year, not this year, understanding how these dunes form, what is their composition, what is the mechanism, what is the chemistry, and so on. We came to what we call Murray Butte. It's very spectacular. No way, I mean, you can really see that these are strata. These different strata tell you a story about Mars. So we're making progress with Curiosity. ChemCam, our instrument from US and France, is working fine, firing the laser. So we fire once, twice, and so on. And as of yesterday, we fire 423,000 times. So it's getting okay. Approximately 363 shots per soul these days. Each time we fire, we measure the composition. This is, for example, what we call the major elements: silicon, titanium, aluminum, iron, magnesium, calcium, sodium, and potassium. We're also looking at minor elements like lithium, rubidium, strontium, barium, and so on. So this is really an instrument that measures the composition of the rocks and soils on Mars. So we're doing our physics. So I'm not going to give you results. I don't have enough time, but if you put, for example, that's a simple one. You shoot on the rock on the left, and then you shoot. At some point, you shoot on the white part, and then it's black again. And when you shoot on the white part, you can see that, oh, it's calcium, sulfur. It's a calcium sulfur. Well, what does that tell us? When we study, we find out it's bosonite. Bosonite it's a form of dehydrated gypsum. You heard about gypsum. What's important is not gypsum. What's important is that to recreate that, I have to imagine that at some point there was a crack into the rock, and the crack was filled with liquid water. And the liquid water was probably at 50 degrees C. So what the calcium sulfate tells me is that it was just hot liquid water. And that's the interesting part. So we do our chemistry, and we keep doing that with our everyone. That was one of students we were shooting at rock, and suddenly we were shooting at this one, and she said, "Oh, stop!" I said, "What?" She said, "We've seen manganese." I said, "Wow, manganese, what does it tell us?" We were not really sure, but it was really high manganese. So we studied. We told the rover guy, said, "Stop!" And they don't like when we stop, because we need to drive. I said, "Yeah, it's something interesting, shoot again." So we shoot like crazy on this rock, and then we went by. And we know that manganese, when you have a coating of manganese, it means that there was oxygen in the atmosphere. That's all. Manganese is interesting. Oxygen is in the atmosphere, it's amazing. We don't understand the story, by the way. We don't understand why there was oxygen. But that's a fact. I mean, we have to be driven by the fact, by the data. So we showed that. So we put in pieces one after the other. Sometimes they make sense, sometimes they don't. Most of the time they don't. We do drills. One of our students here used to be in this school, William Rapin, just finished his thesis 3 weeks ago, or a month ago. He loves doing that. I told him, you know, we're drilling with a drill. He said, why don't I shoot with the laser in the drill? So he spent a lot of time shooting at the inside of the drill hole. He's very good at that now. He's really getting small scale. You're shooting at things with an accuracy less than 1 millimeter. Okay, remember, a planet is far away. Okay, so we're really doing small scale physics now, and we're learning a lot from Mars. Okay, back now. How do we put all the Curiosity are all the results from curiosity into the main theme of habitability. I'm going to talk about habitability and taphonomy. Wow, that's a name. Okay, habitability, what is it? You learned that at school. Habitability are all the physical and parameters, I mean, chemistry and physics that you need to have to get life. We don't say we have life, but we say, well, to get life, we need at least water, liquid water, of course, low salt, moderate pH, long-lasting. It's not good. We don't need water for 2 days, okay? We really need water for a long time. Moderate pH is very important, of course. We need what we call the SNOPs, or carbon, nitrogen, oxygen, phosphorus, sulfur, which are some organics, that the building blocks of organics, and we need energy. If you have the three of them, and they will lack the energy from a chemical reaction, and we call that the common heterotroph. If you find them, all of them, at the same time, that's important. I mean, same instant geologic time, you can say this was an habitable world. Okay. At the same time, I'm going to talk about taphonomy. Taphonomy is okay. Let's imagine that I build up organics. What are the chances that I preserve these organics? The science to preserve things is called taphonomy. We need to work on the arrangement of organics, how they're going to survive, because when you are in a sediment, the sediment very slowly is going to turn into a rock, okay? That's called the lithification. That's how you turn a sediment into a rock. How are the organics going to survive that process? How are they going to survive further degradation by cosmic rays? That is the theme of that taphonomy. And for that, we know that from Earth's experience that not all the rocks are good for that. Some of them are better. We found them, for example, in 54, that was the first discovery that in chert. Chert is a very special rock that is very good to preserve organics with time. Now if I go to Mars, I want to find a chert. Okay, because I know this is probably the best place. It's not the best place to have it. It's the best place to preserve it. Okay, and for some reason we lack clays. I told you about phyllosilicates. These are clays and sulfates. They're good too. It's not only to say, well, habitability and organics, but where do I find them? How do I preserve them? Okay, so we went to Yellowknife Bay. It was you've seen it before. It's one of the main stops we did with Curiosity. It was 100, very early in the mission. We did our drill. Actually, it was our first drill. It was very interesting because you see, it was a trial, the first drill, and you can see it's already gray. It's not red, so it's not oxidized surface. That's very good. It's a good start. We did the chemistry with two instruments, chemin, mineralogy, and SAM, cooking, from up to 800 the samples, and we could see the water coming out, and carbon dioxide and everything, oxygen, and we could see sulfur in a reduced and oxidized form. So that's where is our reserve of energy. Here we could see phyllosilicate. Yeah, this is an X-ray experiment. Put everything together, it took us about a few, 2 years actually, no, a little more than a year. We published that in Science. What do we say? There was a liquid water, it was a lake, when phyllosilicates, clays, had formed, and then the calcium sulfate. I told you about that as a precipitate to make the white veins. Okay, a paper by Van Eman said it was a moderate pH, variable redox states of sulfur. Another by McLellan said it was salinity was very low. Ming said we've seen hydrogen. No, that was the low part. We say we think we've seen nitrogen and carbon, but not so much. Grotzinger, our boss, says, well, the conclusion is pretty simple. Yes, Mars was in the past an habitable world. With Curiosity, we have discovered the habitability of Mars. It's a major discovery. Remember that in the solar system, as far as I know, 5 years ago, there was only one habitable world. It was Earth. Now we have two. Well, we had two. The question is Mars still habitable? It's a major question, and it is not, honestly. It is not, because we've lost the liquid water. But so 2 out of 8, that makes quite a statistics, okay? Now if you look at exoplanets, you know you have exoplanets all over, everywhere in the universe. you can say, wow, there must be a lot of habitable world over there. Because I know that around the sun, at least we have 2. So that's really changing the perspective at which you're looking at the universe. There was something that was not done properly onto this habitability, were the organics. We had a student for that, Caroline Fressinet. She was in the US, one of our postdocs. And one of the samples, Cumberland, here, she found chlorobenzene. The chlor part, the chlorine connection, it comes from somewhere else, but the benzene is really local to Mars. And our conclusion in a very nice paper, she said, it was the first discovery of organics on Mars, so it's really closing the loop. Back to taphonomy. So we have discovered habitability, we have organics, so it's looking good. Hassler put a paper on the radiation. He says, well, we may have a problem. If he has a radiation measurement on Curiosity, and he says, look at what he says. He said that in 650 million years, everything that is within the first meter is going to be, everything that is near the surface it's at the surface, is going to be destroyed by cosmic ray. So Tom Fraser will say, even if we had organics, because it was long ago, the cosmic ray should have broken every molecule. So no chance to find traces of complex organics. But at the same time, Ken Farley made a measurement of an age dating. He says, what the age of the rock? So it's kind of a weird measurement, but we think that the rock is around 3.2 plus or minus 350 million years, but it's an old rock. I mean, that place at Yellowknife, okay, no, at Cumberland actually, Cumberland. But at the same time, he said, this rock has been exposed only for 78 million years. So it's an old rock, but it was deep underground. Because of erosion, it was exposed only 78 million years ago, which is far below the 650 we've seen before. So we think we have chances to preserve some organics at Mars. Okay, so we think we have a story now to do it. So make it short as a story. There was a time where there was water. Clearly, there was water into this big crater. So the crater has been built by impact, filled with water, and later on filled by sediments, to the point where sediments were filling everything, even more than everything, because there was a cap with something like, starting with a dune, but making bigger and bigger, so alien deposit, and then it was eroded again by wind, and that's where we are now. So we're putting together the story, but very clearly it was an habitable world. So conclusion, Mars habitability has been demonstrated at Gale, thanks mostly to Sam and Kevin, our 2 laboratories. It required approximately more than 300 scientists to do that. I didn't say much about perchlorate, but there are perchlorates in the soil, and that doesn't help, because when we do the chemistry and each of the sample, the perchlorate destroys the sample at the same time, so it doesn't make our life easy. Robotics makes the process very slow, and of course where we landed was more complex than we saw. So open question, for how long was Gale crater an habitable world? We don't know, we need to work that. Okay. Is it habitability at Gale only? Well, we don't know. We need to go somewhere else. That's easy, so we're going to do another couple of good missions. Why did the habitability stop? Haha, that's important. Why did it stop? And what about today? Do we still have habitability today? So very quickly, habitability today, some people say, yeah, maybe there's even more than that. We've seen CH4, methanes. You know that methane on Earth is produced at 95% by bioactivity. Okay? 5% is produced by the reaction of olivine and hot water that create methane. It's working fine on Earth at the tectonics, when the plates are going under, it's producing a lot of methane into the ocean. We know that. But on Mars, there's no plate tectonic, there's no hot spot, there's no liquid water today. It's hard to explain why would we have any CH4 on Mars, except maybe bio CH4. And we've seen CH4. Yes, we saw it from orbit, and a lot of conflicted results. It was not very uniform, it was local. We don't know, we have a hard time to interpret that, but you have to understand that CH4, today I put a molecule of methane on Mars, is going to, its lifetime is 300 years only. So if I see it today, it's being produced today. That's a key point of methane on Mars. And so what did we see with Curiosity? We saw almost nothing, 0, and you see this is measured by tunable laser inside of SAM. The units are in ppb per volume, part per billion. Okay, take a billion of molecule, 1 is a CH4. Okay, the measurement we have on average is less than 1. But suddenly, one day, when it was a certain period of time, we see a burst of CH4. We don't know where that comes from. Have we seen bioactivity on Mars? Honestly, I don't think so. There's a reason for that. Is that you know that just like on Earth, meteorites are striking the planet. On Earth, we have meteorites. We could have comets, for example, some more water, or volatiles. And when we do modeling, we say, well, that's actually, it's even more than that. We think that the measurement we see now, the measurements on average, is 3 times lower than the input for meteorites. So actually we don't find enough CH4. Okay? But that's probably a problem in the model. So we cannot say we've discovered CH4 that would come from Mars. Except when we have this burst, and we don't know, maybe we walk on something and crack a rock and there was a small pocket of CH4 under the ground, we don't know. So, still not open topic, but no, Mars is not an habitable world these days. I don't think there is life, even if CH4 is a puzzling problem. And one last thing is to explain why did the habitability stop. We have to look at the atmosphere, and for that, you have a spacecraft that arrived 2 years ago. It's called MAVEN. It goes inside the atmosphere, outside, inside, outside. So it's looking at the interaction of the layer between the atmosphere and the solar wind. And the solar wind is really escaping our atmosphere of the planet. It's really, and the rate now, we know the rate. The erosion rate is approximately 100 grams per second. It's big. If you extrapolate that onto the lifetime of Mars, well, you say, well, yeah, it makes sense. Maybe it's just because the planet did not have any magnetic field, no shield to protect against the solar wind, the atmosphere has disappeared. So we think we have an idea now, how did the atmosphere disappear? Slowly because of solar wind. Too bad it didn't have a magnetic field. Why did it didn't have a magnetic field? Well, we need another mission. It's going to be called SICE. Okay, I'm sure InSight will tell us about the internal structure of Mars, and maybe we understand why there was no magnetic field. So you see that it's coming together. So I'm finished in a minute. The next one is Mars 2020. We're building that. It's a big one. But it's bigger than Curiosity. Curiosity was 900 kilos, that's 1100 kilos. We're building an instrument in France, again, top of the mass. We call it SuperCam. It's going to do chemistry, mineralogy, and you see, fun part, there's a drone. It's called the helicopter. So we're going to find a drone on Mars. The wings are probably that big, but the drone is that big, okay? There's only a camera on board. It's more technology than science, but it's fun. So there'll be a drone, a big rover, great story. I should do that. The part is doing the cache. So the cache, again, is we're going to walk around the planet everywhere, try to get these small tubes, very tiny ones, put them in a jar, and we call it sample cache, and put the sample cache on the ground. Okay? And next, it's your generation to go and get it back. It is meant to survive for 20 years. So I give you 20 years to get it back. Okay? It's not going to be me. Okay? And what we're going to do next week, next week, I'm flying tomorrow, do a little bit of fixing on Curiosity, and at the same time, also going to work on Mars 2020, and we're going to decide where we're going to land. That's very important. We have so far 8 different landing sites. We need to pick up one. So we do just like here, put all the scientists that knows about Mars, say, where do you want to go? And you have to fight, like crazy. I want to go there, where there. We vote, we try to explain each other what's a good one. I don't know which one is going to pick up, I have my idea, but this is where we are so far. So, it's on its track, Curiosity is fine. I didn't talk about much ExoMars, but we now have the money to go to the end of ExoMars, so that's good news. Mars 2020, InSight. Again, we are really, it's probably the most exciting time ever on Mars these days, so it's great, thank you. Question.
Just only 2 or 3 questions, then we will go to lunch.
Questions?
I was wondering about, you said that a Mars return sampling mission would be very expensive. Wouldn't it be better to spend this money on a manned mission and return a lot more sample?
Okay. 2 things. Yes. Return sample is a lot of money. Okay. We don't know where, but it's probably 5, maybe 5 billion. Okay. It's expensive. It's a lot of money. Man on Mars so far is 300, and we're not sure we can make it for less than 500. But okay. So we're talking by 2 orders of magnitude. Okay, that's first point. But it's a good question. Second is that the day we land a man on Mars, science of life is finished. Okay? I'm not going to look for traces of life with a man. Man is life. Okay? It's going to bring life. Okay? It's over. No, we don't do any science of life after the first man have landed. It's pollution. So, we need to do our science, and there are places for both of us on Mars, of course. And but you get a good point. But it's a lot of money. But putting a man on Mars, it's not a lot of money. It's enormous. There's nothing I can compare to. We need all the different countries to commit for that. It's not a good time these days to get a commitment for so much money. So I don't know how it's going to happen. It will happen for sure, and I hope so.
How do you schedule rover activities on Mars? Do you have like a special time, like per sol or something, or do you just schedule it somehow?
Yeah, driving a rover on Mars is a day-to-day activity. It's not real time. It's too far. Really, the loop is about 24 hours. So the rovers on Mars is doing its activity, and it sends us data. So send data to the orbiter, so maybe to Mars Odyssey. So Mars Odyssey is getting the data, and a couple of hours later, send them back to Earth. We receive the data, we study the data, then we have approximately 8 hours to decide what we're going to do tomorrow. We decide, are we going to drive? Are we going to deploy the arm? Are we going to drill? We're going to shoot the laser, take images. We have a certain amount of energy, certain amount of data rate, how much data we can return. So it's very constrained. So we do that for 8 hours, then we send the plan to the rover. The rover receives the plan, they say, okay, now it's time to go. I drive, I shoot, I send the data up, I drive, I scoop, and well, at night, it's most of no driving at night, too cold. So you see that it's a process that is complex, that is slow. It requires today approximately 110 people every day to drive Curiosity. That's not a simple one. It's very difficult to drive. And out of this is probably 10 people in France every day.
Okay. Last question.
How can you be sure that a sample of meteorite comes from Mars?
Yeah, well, we never sure. But as scientists, but that's pretty simple actually. This part is pretty simple. When you look at meteorites, most of them come from what we call pristine body that have not changed since the beginning of the solar system. So small rocks that come from asteroid. When they come from a planet, they're very different. You know that on a planet there's something we call gravitational sorting, okay? Which means that on Earth today, if I put a rock on Earth, and at the time where Earth was probably a hot planet, and slowly the heavy elements will go down to the core of the planet, and only the light one. So when we see a meteorite, we know if it's coming from a big body or a small body. So we say, oh, that one comes from a planet. And it can only be Mars or potentially Venus. So, I have a rock now, I say it's coming from a planet. And I look at the composition. I know the composition of Mars, of the atmosphere. I'm sorry. And I know the composition, and that's how I get the story. So it's this part we know it. What's interesting is that people find these meteorites, and they feel them. They know them and say, they come from Mars. And when they come from Mars, they're very expensive. They're so expensive that we cannot buy them in our lab. They're too expensive for us. They cost millions, and they go to private collections. But to find that they really come from Mars, they need us. So they have to give us 10%. So they give us 10% of the mass. We have to prove it's coming from Mars. This is what we use for science, and 90% are going to private collections.
Thank you.
Thank you.